Hello friends, I welcome you on my channel Engineering Mathematics DJ Ganit. In this lecture we are going to discuss some more examples on implicit differentiation for partial derivatives. So we start with example number 1. If cos x to the power y equal to sin y to the power x, find dy by dx. So here we are given implicit relationship between the variables x and y, and it is assumed that this relationship determines y as a function of x. So we are asked to find out ordinary derivative of y with respect to x. So as we know, first we will consider this equation by taking all the non-zero terms on left hand side. So this we can rewrite as cos x raised to y minus sin y raised to x equal to 0, and we assume that this left hand side is function of x and y denoted by capital F, and we find out partial derivatives of this function capital F with respect to x and y. So del f by del x is, here we have to apply chain rule. Derivative of y power is y into base raised to y minus 1 into derivative of base function, which is cos x, and derivative of cos x is minus sin x, and here we have sin y raised to x. So we have to apply this formula del by del x of sin y raised to x. So it is similar to this formula. Derivative of a raised to x is given by a raised to x into log a. So here instead of a we have sin y. So first we write down sin y raised to x into log of sin y. So we take a equal to sin y in this formula for this derivative. Now we rewrite this as fx equal to, we consider this negative sign outside these brackets. So we have minus y sin x cos x raised to y minus 1, and we keep this as it is, sin y raised to x log sin y. Similarly we differentiate this function with respect to y. So for derivative of cos x raised to y with respect to y, we will use this formula with a equal to cos x. So if we take a equal to cos x and instead of x we have y, so it is cos x to the power y into log of cos y. So derivative of cos x raised to y is cos x to the power y into logarithm of cos x, and derivative of sin y raised to x with respect to y is, here x becomes constant, so we take x power outside, and in the power we write x minus 1, and in the product we have to differentiate sin y with respect to y, so it is cos y, and we rewrite this as del f by del y equal to cos x raised to y log cos x minus, here we take cos y with x into cos y sin y raised to x minus 1. So now we use the formula for implicit differentiation. As we know, dy by dx is given by this formula, negative of del f by del x over del f by del y. So we substitute values of del f by del x and del f by del y in this formula. Now here we can write cos x raised to y minus 1 as cos x raised to y divided by cos x, and same thing here, sin y raised to x minus 1 can be written as sin y raised to x divided by sin y, and here we take this negative sign outside, so negative will be positive. Now if we observe here, we have sin x over cos x, so that we can rewrite as tan x. Similarly in the denominator, cos y over sin y, that we replace by cot y, and if we observe that given equation is cos x raised to y equal to sin y raised to x. So we replace cos x raised to y by sin y raised to x, and other things we keep as it is. So here sin x by cos x is tan x, cos x raised to y is sin y raised to x. We keep this term as it is. Here we replace cos x raised to y by sin y raised to x into log cos x minus x times cos y over sin y is replaced by cot y, sin y raised to x as it is. Now in the numerator, from these two terms we can take sin y raised to x common, and same thing from the denominator. So sin y raised to x can be cancelled out, and we are left with y tan x plus log sin y over log cos x minus x cot y. So this is the derivative of y with respect to x from the given implicit relation. We consider one more example. We are asked to find out dy by dx using partial derivatives. That is, we have to use this formula only. Dy by dx equal to minus fx over fy, and this is the relationship between x and y, and we have to find out dy by dx at x equal to 0, y equal to log 2. So here also this relationship determines y as a function of x. So first we assume that this left hand side is denoted by capital F, and we calculate partial derivatives of capital F with respect to x and y. So while differentiating with respect to x, we consider y as constant. So in first term e raised to y is constant, derivative of x is 1. In second term, derivative of sine function is cos function, and in the product we have to differentiate x into y with respect to x. So for that y is constant and derivative of x is 1, so it is y into cos xy, and there is no x here, so derivative of this term with respect to x is 0. Now del f by del y. So here for del f by del y we consider x as constant. So x as it is, derivative of e raised to y is e raised to y. Derivative of sine function is cos function, and derivative of x into y with respect to y is x, and derivative of y is 1, and derivative of log 2 is 0. Now we substitute these two values in this formula. Dy by dx is given by minus fx over fy, so we put fx equal to this and fy equal to this. Now we are asked to find out value at this point, x equal to 0, y equal to log 2. So in the right hand side we put x equal to 0 and y equal to log 2. So dy by dx at x equal to 0, y equal to log 2 is e raised to log 2 plus log 2 cosine of 0 into log 2, which is 0. Here x is 0, so this term becomes 0, this is also 0, and plus 1. Now e raised to log 2 is nothing but 2, and plus log 2 cos 0 is 1, and negative side. So dy by dx at this point is nothing but negative of 2 plus log 2. Now before going for another examples, we make one remark. We have seen this formula in previous lecture. If we have implicit relationship between the three variables x, y and z, and suppose this relationship defines z as a function of x and y, then at points where del f by del z is non-zero, del z by del x is given by minus fx over fz, and del z by del y is given by minus fy over fz. So here we are interested in the partial derivatives of z with respect to x and y, and we have discussed this formula in previous lecture. So del z by del x, to find out del z by del x, we have to consider del f by del z in the division. And if we want to find out del z by del x, here we will write down partial derivative of capital F with respect to x, and here we will write down partial derivative of capital F with respect to y if we are interested in del z by del y. Now suppose instead of this situation, suppose this implicit relationship determines y as a function of x and z, then we are interested in partial derivatives of y with respect to x and with respect to z. So what will be the corresponding formula for these two derivatives? So if we are interested in partial derivatives of y, as we have written this formula, we have to divide by del f by del y, and here we are interested in the derivative with respect to z. So here we consider partial derivative of f with respect to z. Similarly, here we are interested in derivative with respect to x. So here we are writing del f by del x. So in this way we can develop another two formulas. We don't have to cram the things, we just apply this logic that here we are interested in partial derivatives of z with respect to x, so we divide by del f by del z. And here if we have x, we consider derivative with respect to x, and if we have y here, we consider derivative of capital F with respect to y. So we write down the formula for other two partial derivatives. If the equation f of xy equal to z, f of xyz equal to 0 determines y as a differentiable function of x and z, that is, suppose y is an implicit function of x and z, then at points where del f by del y is non-zero, we can find out partial derivatives of y with respect to x and z using these two formulas. Del y by del x is negative of fx over fy, and del y by del z is negative of fz over fy. So here also we are interested in the derivatives of y, so we are dividing by del f by del y, and here we have derivative with respect to x, so we consider del f by del x here, and here we have derivative with respect to z, so we consider del f by del z here. Similarly, suppose x is a function of other two variables y and z, then we can find out derivatives of x with respect to y and z. So suppose the equation capital F of xyz equal to 0 determines x as a differentiable function of y and z, that is, x is a function of y and z, then at points where del f by del x is non-zero, we can write down the formulas for partial derivatives of x with respect to y and with respect to z as written here. We are interested in the partial derivatives of x, so we divide by del f by del x, and here we are interested in the derivative with respect to y, therefore we write del f by del y here. Here we are interested in the derivative with respect to z, so here we write del f by del z. So in this way we can write down the formulas for implicit functions. So we consider one example. Find the value of del x by del z at the point 1 minus 1 minus 3 if this equation determines or defines x as a function of the two independent variables y and z. That means x is an implicit function of y and z given by this relationship, and it is given that partial derivative exists. So we are interested in the partial derivative of x with respect to z. So first we assume that left hand side is capital F of x y z. So suppose capital F of x y z is x into z plus y log x minus x square plus 4, and we are interested in the partial derivative of x with respect to z. So because we are interested in the derivative of x, we divide by del f by del x, and because we are interested in the derivative with respect to z, here we write fz. So we first find out del f by del x and del f by del z. So del f by del x is, we consider y and z as constant. So in the first term z is constant, derivative of x is 1. Here y is constant, derivative of log x is 1 by x minus derivative of x square is 2x and plus 0. Del f by del z is x is constant, derivative of z is 1, and in remaining terms there is no z, so derivative of those terms with respect to z is 0. Now we put values of these derivatives in this formula. Del x by del z is minus fz by fx. Here we put fx equal to this and fz is x, and we are asked to find out del x by del z at this point. So we put x equal to 1, y equal to minus 1 and z equal to minus 3. So after simplifying, we can see we have 1 over, this is minus 3 minus 1 minus 2. So it is 3 plus 1 plus 2, 6. So it is minus 1 by 6. And here negative sign, so we have 1 by 6. So implicit derivative of x with respect to z at point 1 minus 1 minus 3 is 1 by 6. Now if we don't want to go by this formula, we can find out directly derivative of x with respect to z. For that we have to differentiate given equation with respect to z on both sides. We are asked to find out del x by del z. So another way to do this problem is we differentiate whole equation both sides with respect to z, and we will keep in mind that x is a function of y and z. So derivative of first term is, here we have to apply product rule because x is a function of y and z. So first x as it is, derivative of z with respect to z is 1, and plus z as it is, derivative of x with respect to z, which is del x by del z. So that we have written here x as it is, derivative of z is 1 plus z as it is, here we have to write del x by del z, plus y as it is, because derivative is with respect to z, so we consider y as constant, derivative of log x with respect to x is, derivative of log x with respect to z, and x is function of y and z. So here we are applying chain rule. First we differentiate log x with respect to x, and in the product we write down derivative of x with respect to z. So derivative of log x with respect to z is 1 by x times del x by del z, and derivative of x square is 2x times del x by del z by chain rule. Now we collect the terms which contain del x by del z. So del x by del z is common, and we will have z plus y by x minus 2x into del x by del z, and we consider this x on right hand side. So therefore del x by del z is negative of x over z plus y by x minus 2x, and we find out value at a given point. So we put x equal to 1, y equal to minus 1 and z equal to minus 3, and we obtain same answer minus 1 by 6 and negative sign, so we have 1 by 6. So if we wish, we can go in this way also, that is our choice. Either we can use the formulas for implicit derivatives, or we can directly differentiate given equation with respect to given variable. We consider one more example. Use implicit differentiation to find del z by del x and del z by del y if sin of xyz equal to x plus 2y plus 3z. So we start by assuming this given equation can be rewritten as sin of xyz minus x minus 2y minus 3z equal to 0, and we assume that left hand side is denoted by capital F, which is function of xyz. Now to find out these two derivatives, we recall the formulas for del z by del x. We are interested in the derivatives of z, so we have to divide by del f by del z, and here derivative is with respect to x, so here we consider del f by del x. Here derivative is with respect to y, so here we consider del f by del y. So first we find out these partial derivatives of f with respect to x, y, z by considering x, y, z as independent variables. So del f by del x is derivative of sine function is cos function into derivative of this x, y, z with respect to x. So y into z is constant, derivative of x is 1, minus derivative of x, which is 1, and derivative of these two terms is 0 because they do not contain x. Similarly, del f by del y is derivative of sine function, which is cos xyz, into derivative of xyz with respect to y. So x into z constant, derivative of y is 1, and derivative of minus 2y is minus 2, derivative of these two terms with respect to y is 0, and del f by del z is derivative of sine function, which is cos xyz, into derivative of xyz with respect to z. So x into y is constant, derivative of z is 1, and derivative of minus x minus 2y with respect to z is 0, and derivative of minus 3z is minus 3. So now we put these values in the formulas. Del z by del x is minus fx by fz, and if we put values of these derivatives here, del f by del x is yz cos xyz minus 1, and del f by del z is xy cos xyz minus 3, and if we take this negative sign inside the numerator, we can rewrite numerator as 1 minus yz cos xyz over xy cos xyz minus 3. Similarly, we can write down del z by del y. We have substituted values here, and we have taken this negative sign inside the numerator, and we obtain del z by del y equal to 2 minus xz cos xyz over xy cos xyz minus 3. So in this way we can find out derivatives from the given implicit relation between the variables. So we have seen this type of things in this topic of implicit differentiation. If we have this relationship between x and y, and suppose y is a function of x, then dy by dx is given by minus fx over fy, and d square y by dx square is given by cube of q square into r minus 2 pqs plus p square into t, and negative of this, where we assume that small p is del f by del x, small q is del f by del y, small r is second derivative with respect to x, small s is second derivative with respect to xy, and t is second derivative with respect to y. and if we use p and q for these derivatives, we can write dy by dx equal to p by q also. So from this relationship, implicit relationship between x and y, where y is a function of x, we can find out dy by dx and d square y by dx square using these two formulas. Similarly, if we have a relationship between three variables, say f of xyz equal to 0, and depending on different cases, suppose z is an implicit function of x and y, we will have partial derivatives of z with respect to x and y, which are given by these formulas. We are interested in the derivatives of z, so we divide by derivatives of z, and here we have x, so we write del f by del x here. Here we have y, so we write del f by del y. Now suppose this relationship determines y as a function of x and z, then we are interested in the derivatives of y with respect to x and z. So similarly, we have the formulas for derivatives of y with respect to x and z. So this is the way how we will remember. We are interested in the derivatives of y with respect to x and z. So we require derivatives of y, so we divide by del f by del y, and here we have x, so here we write partial derivative of f with respect to x, and here we have z, so here we write partial derivative of f with respect to z. And at last we have seen this also. Suppose x is a function of y and z, then derivatives of x with respect to y and z can be written in this way. We are interested in the derivatives of x, so we divide by x, and here we require derivative with respect to y, so here we have del f by del y, and here we have del f by del z because we have z here. So this is all about implicit differentiation in this topic of partial derivatives. So I hope you like this lecture. Thank you very much.